Right. So we said our issue last time is that all of the oxygens are nucleophilic. However, there is a slight solution where we can selectively react one of the oxygens. And that has to do with only one of these oxygens forms a good leaving group. And so what we're going to do is form these glycoside bonds or glycosidic bonds. And so let's take a look at what we're going to do here. And it's going to be our alcohol attached to our anomeric carbon, because if we think about what can happen here, if we add some kind of H plus and then an ROH, what can happen is that this alcohol can pick up an H plus. Nothing magical there. Right, and this is also the hemiacetal position. And now what can happen is the lone pair from this guy right here can form a pi bond and then kick off this water group. And so this is the kind of star resonance form, right? The star of our show. And what allows us to selectively act in this position, right? It's because we can form this resonance stabilized carbocation that no other position can form. And then what we can have is just a nucleophile attack that position. To selectively add or selectively replace that position. So let's take a look at it. And again, the hemiacetal position is going to be reactive because the intermediate, that carbocation, is resonance stabilized. Whereas a regular alcohol is going to be unreactive, or at least less reactive, right? Because it does not have a resonance stabilized intermediate. So for example, when we take our glucose molecule, and again, we add some HCl, and then we add a nucleophile like methanol. That way, this guy is going to act as an electrophile and not a nucleophile. We will selectively add that methoxy group onto that hemiacetal position. Right, so the rest of these will be untouched. And then that one will go there. Right, and that methyl group will go right there. And then if you think about the mechanism, right, we have this kind of sp2 hybridized intermediate. So the nucleophile can attack from either position. So we'll get both anomers, right? In this case, what I drew was the beta, but you'll get the alpha one as well. Overall, this is very common in nature. So what we have over here to the left is a trisaccharide. And it's made out of 1, 2, 3 saccharides, right? There's your 3 six-membered cyclic sugars. Note that this is yet another way that we can draw these, right? Just the old school cyclohexanes with wedges and dashes. And then note that all of these right here are glycosidic bonds. Right, so that's how they form these polysaccharides and how they attach other things to them as well, right? Carbohydrates can do more than just provide energy. So in this case, there's a steroid attached, and then this can go ahead and transport it to some other part of your body. Again, biochemistry, everything is extremely complicated, and what you need to know really depends on the system that you're studying.